So, welcome back, or hello for all people joining for the second part only of the session. This part is about MLR3 and spatial modeling, and I'm Patrick, one of the MLR core team members and main developers of the spatial extensions. And I will walk you through what MLR3 has to offer. This is what we will cover. Just a general intro about MLR3 and spatial temporal data. And then more specifically, I will talk about the MLR3 spatial and MLR3 spatial temp CV packages. We'll also have a hands-on part. And this will be as long as there's time left from my previous talking about the slides. And afterwards, as well, some use case introduction from about ensemble modeling from Leandro. Time-wise, we'll see how it goes and how much time we have for the hands-on part and for the use case. But let's get going in the first place. So what we will not talk about in this part, because we have covered it in the first section already, is general building blocks of MLR and machine learning, like task learners, tuners, dictionaries, pipelines, graphs, and whatnot. They are explained in our book or in the gallery. You can also find use case examples about in there. But if you already have basic knowledge that you have either gathered from the first block or you had them before, you should be good for the session. So don't worry. So MLR3 and spatial temporal data. So we will cover what we need to be aware of, what is still missing in the framework, what options there are for contributions, and how MLR3 can in general help for spatial temporal data, which applies to environmental modeling, ecological modeling, all kinds of modeling that involves spatial and spatial temporal data. So we have essentially two big packages, or well, I'm not sure if you should call them big, but that covers this space. This is first MLR3 spatial temp CV, which provides resampling methods, for example, for cross-validation, spatial temporal resampling methods. And then there's MLR3 spatial, which is our package for spatial data backends, and parallelized prediction support for spatial data. There's also MLR3 temporal, which stands on the side of MLR3 spatial, that is aimed to support temporal data backends and time series and whatnot. But unfortunately, I neither have time nor, I would say, the knowledge to also do this package, because I haven't done much of time series processing, other things. So this is not really usable right now. Some people on our team try to start it a bit, but I haven't had time as well. So if you're interested or know somebody else that could potentially be interested in pushing this forward and creating this extension, bringing it to a usable level, just reach out to us. We're open to everything. And this is also, by the way, how I got started back then in the days with MLR. I wanted to do spatial modeling. I wanted to use a framework. There were no spatial extensions available. I talked to the MLR guys back then. I contributed some stuff, and this is what came out after a few years. So everybody can get involved and can get started. And we're not a closed group or anything like that. So it's just an open source teamwork of various people that just like to do these things. So MLR3 spatial, what's inside the tin? We have data backends for raster data, for raster bricks, raster stacks for the raster package, for the spot raster class from Terra, and also for the stars package. So this covers pretty much all the spatial backend space in R. Then for vector data, we support SF objects, which is the de facto standard in R for vector data. And you can use this We have the as-task classic converters for input data, because usually, in most of the cases, you start with some point observations for your task that you train your model on, and usually then you predict maybe onto a raster or something else. So you can use these class converters to easily get started there without having to worry about removing the spatial part of the objects. So you can just input as objects. So in addition, we try to help a bit with prediction. What does that mean? You already know from the first part that we rely on future in the MNR3 package. So what we do here is as well, we make use of future for parallel predictions via predict spatial, and we do things a bit differently. The main point that we do differently, and that is actually one of the features, is that we are able to do memory-aware chunk predictions. What does that mean? So usually it depends on where you execute a prediction, but if you do it on a large image, at some point you might run into memory problems, especially if the image is big, or if you do a lot of predictions, and also depending on how much memory your learner uses, you might not be able to do this all in one predict call, because your session might just crash because your memory overflows. What we can do here is we've implemented some guardrails so that things might be slower because you do it in chunks, but these chunks ensure that your session doesn't crash and you can stay within your memory limits of your respective machine. So we don't do everything in one big chunk if you want to do so, but we chunk it, and you can also control the chunk size. And the same applies for the parallel. So you can, of course, then execute those chunks in parallel. Of course, it's better and faster the more prediction values you put into one chunk, because then you don't have too much splitting. But this is something that is available via the predict spatial function here. So here's a nutshell example again. So we create a task classic ST. ST here stands for spatial temporal. And yes, this is a subclass of the task classic that we've operated on before. This is because for spatial data, we have additional metadata information, the data that we want to store in our task. And the normal task classic doesn't know anything about these. It doesn't know about spatial data, about coordinates, about whatever. But task classic ST does. And that's why we use it. We use the land cover as the response here. And again, we train a random forest on the data. And yeah, you're already familiar most likely with the syntax. So we use the learner sugar function to create a classic ranger learner. We read the external data here from our package. We create a task and we train the learner task. So far so good, nothing unusual. The only difference is that we have a spatial task that is aware that it has coordinates, which are by default not used as features. They are treated as coordinates, maybe used in the resampling, but not used in training. If you want to do so, you can do that by using a flag to include them, but usually you don't do that. So then once you have trained your learner, you want to predict your learner on an image. And here we load an image with the Terra package that is also included in the package. And what we do then in line number 3 is that we create an unsupervised task on that input data. And we use this unsupervised task as an input for the predict spatial function. You might ask yourself, why can't I just input directly my TIFF into the predict spatial function? Can't you handle that internally? The answer is yes and no, maybe a bit of everything. So yes, we could eventually handle that internally. Why do we need a task in the first place? Because for some operations that happen internally, we need the task information and the metadata around it. And we need a task to operate on certain internal functions. And if you only pass us spatial objects, sometimes there might be something missing that is actually within the task automatically extracted. So we might change this in the future, maybe simplify a bit, but for now, this is how it goes. Yeah.
Have you benchmarked this versus just using like, I don't know, in RAM R objects to predict like raster or spatial data frame?
Yeah, I think, yes, what you referring to, I will show a few slides later.
Okay, thanks.
But what you see here first in the output, right, is that we do the raster prediction. And you see also here that this chunk line that I talked about. So by default, we will execute the prediction with a chunk size of 200 megabytes. So we will split the image into chunks of 200 megabytes that will be executed. And these chunks, it also prints out how many values are in this chunk. Of course, the values count depends on the resolution of the image. Then
one more thing, can you have in the Leipzig raster, can you have also classes? There's a covariate, you know, like
you can have everything in there, right?
Okay.
It's just right. It just must have to match your model that you trained on,
okay.
Right? So in the end, the only difference is that it's not a tabular input format that you use here, and we save you from the pain of converting all of the information in the raster to tabular format and then using this for prediction and then converting it back again. So that's what we save you. Because in the end, what you get as an output here, you see you get again a spot raster. You can, by the way, also have, there's an argument in the predict spatial where you can directly set what kind of format you want to get returned. So you can get spot raster, you can get a stars object or a raster object, depending on your preference.
And what if you're missing values in the pixels?
Then they are treated in the same way as they would be treated as missing values in a normal prediction. So either your learner can handle that or not. I think it depends on the learner. And of course, you can also set certain actions of how a learner should act on missing values or not, if the prediction is skipped or if it cannot do anything or.
Like in the MLR, I remember there were many problems, like you have to sort the features exactly, you have to remove all the missing values.
That highly depends on the learner that you use. So some learners can cope with it, some not. Some need dummy encoded factor variables, right? Should boost, some others not. That depends on the learner, but it's not specific to the spatial thing. But of course, let's say the quality of your image matters, right? Because we can only use what's inside. And if there's a value for a pixel, we can use it. If not, not.
But let's then say the easiest thing is just make sure you remove the missing values or fill them in, and make sure that the order of features and the structure is exactly like in the.
Yes, in the end, what is in your image gets into the prediction and is then treated in the tabular format. And the nice thing about the Terra package that we use here is that it properly handles factor variables, which is important if you come directly from the image, because the raster package didn't do so well on doing that, because that's what we need in the end to be able to distinguish between numerics, factor variables, and all the normal stuff that you have on the tabular side, which is sometimes not so easy to handle if you just deal with the image objects. But other than that, essentially, we try to get the pain away from you by saving you from converting from image to tabular data and then back and doing all this round trip. And yeah, this is what we try to do here. And after that, we can again offer just use the default plot function for the spot raster. And we see here our output, if we color it a bit, is, by the way, located in the northwest of Leipzig. And we see that this has been predicted in the image with the classes because they the Terra now meanwhile properly handles factor variables, and we just get a very good output that shows our prediction with the classes that we predicted on. And if you go back, I mean, this is, even though this is of course a toy example, it really shows how few lines of code you can achieve this without converting back between tabular formats, image formats back here and there, and potentially also do this in parallel, but we'll come to that. So when I started out back then, that's why I pointed it out, this was actually the pain I was always coming across. So, I mean, either you stay in the world of using the direct predict function of your spatial package like Raster or Terra or something else, but then you had maybe trained your learner in a framework, and then you had to maybe access this learner, and then, but you have to predict it. Actually, you want to predict it with the predict function of the framework, but that doesn't really work, but you need to use the one from the spatial package, and then you always work between those two worlds. And I just wanted to have a way to treat spatial data and predict spatial data within the framework in the same way as you would treat other building blocks of machine learning and MLR. And I don't wanted to convert always between the formats and potentially maybe lose coordinate information, have to reattach them and whatnot. So what is the problem about predictions and especially spatial predictions? So spatial predictions can take quite some time, because if you have a high resolution and a large image, you have a lot of pixels that you need to predict on. And a lot of, pixels in the end, you can treat them as points if you're in your mind, right? That you want to just have a prediction for using your learner that you've trained. And it doesn't really matter if you do that in the end in an image, or if you convert the image first to tabular data or whatnot, but usually a lot. And there are ways, if you use the native predict functions of, for example, Terra, to also do that in parallel. But usually you have no choice of the parallel backend. You just pass a number for the core value. Something happens in the background. This is similar to what MLR does. But usually you, at least in MLR, have the choice of the backend if you use future. And as said before, you have the option to use memory-aware chunk predictions, which you usually don't have if you use a Terra package, because it does everything at once. And if you have too less memory for your prediction tasks, you will never see a result. And I also put here the term eventually more efficient. And this is maybe something that you referred to, Tom. I also did a benchmarking about using Terra directly and using MLR3. And this is what came out. So what I did is I created a 500 megabyte file of this with roughly 25 million values, 1 meter resolution, 2 layers. That is the function I used. It's in the MLR3 spatial package. And here it's a benchmark. So the lower ones is comparing MLR3 4 cores, Terra 4 cores. The two upper ones are MLR3 all cores and Terra all cores. And of course, such benchmarks, and I want to say this as the first point, always depend on your CPU and how it handles single core and multi-core and how many you have. So some CPUs are better in single core, some others really shine in multi-core. Sometimes you hit an overhead that is so large if you use all cores that you're better off using just half of your cores. It always depends. And if you rerun this vignette or this benchmark that is presented as a vignette as well, you might get different results. And what is also very important here is the choice of the backend, especially if you look at this interesting result here. Is the choice of the backend. Because if I choose a different backend, this one shifts also here. If I would use the same multi-session psocket cluster backend, for example, as the default is as it is the default in the Terra package. So this is using the multi-core forking-based backend that you can only use on Unix systems. But what you also see here is that I have here 4 cores, and by the way, all cores means 8 cores on my machine. That there is only slight difference, right, between MLR3 and Terra if you use 4 cores, and there might even be even more small difference if you would just use 2 cores. But it might also be that the difference between all cores, between Terra and MLR3, depending on the backend you use, might be even larger than shown here. So it really depends. And this might also change over time. So I'm not saying this will, because Terra evolves, future evolves, the backends maybe evolve. And Terra also, by the way, does not have any influence on the backend it uses. It uses the built-in R backends, which also Future in the end does. So Future is not using anything special, but at least Future gives you the choice of the backend selection. But if you see this, right, and we have absolute times of like 20 seconds to 35 seconds here, and my machine is quite fast actually, so it might take a bit longer maybe on yours. But the point is, if you save so much time, and if you see the relative differences here, right, this is almost 2x. I think that's interesting to see and promising for the MLR3 future-based parallel predictions.
So just one more time, can you go back? So they seem on the lower graph, they seem to be more or less the same. There's a little difference.
Mm-hmm.
And the upper one is just the data doesn't get the parallelization.
I'm not sure actually, yes, what happens in the top, because of course, one course.
Robert Heimas was here, he will say he's doing something wrong, probably.
Well, what I mean, we can look up the code. Maybe I did something wrong in the code, but what I did is just putting in, I mean, you cannot do anything else than just putting in an integer value for the num course in the Terra predict function. And I'm not sure, so this is not just one run. I did 3 iterations for each. And we don't see much variance here. So it's not that one just didn't work, but all cores did not work. And maybe, yes, something is wrong here, and maybe something might be fixed in future versions, or maybe I did something wrong, and this shifts also here. And then we don't have much difference here as well. But at least here in the 4 cores, which seems to work, right? We at least see that there's maybe a bit of improvement if you use a different backend here. But again, this might change. This might be different on your machine. This might be different on the use, depending on the backend. And in the end, these are just some numbers. I mean, if you go parallel, you definitely save some time. And you can use MLR3. You can use some other direct predict functions. It's your choice. I mean, we don't do anything fancy here. It's just using future-based parallelization in the backend. We are not responsible for that. We are also not claiming that this is some fancy things, tweaks on our side in the backend. So this is done by other people, essentially, that account for the parallelization implementation. So that's it for MLR3 spatial. So enhanced spatial prediction support, memory-aware chunk predictions, future-based parallel predictions, and the ability to easily use raster data and vector data within MLR3 machine learning pipeline. There is still, of course, probably something missing. Leandro just also notified me about maybe there's some things are not working if you directly access cloud tips from the cloud and use them directly in the model, and maybe we need to add some support there and fix some other issues that things might not work directly. But again, if you try it out and find something, just open an issue, contribute, tell us. We are happy to fix this and make it better. And we need your use cases because we cannot cover the whole space. So then let's talk about MLR3 spatial density. So what does this package do? So this package is providing spatial temporal resampling methods for MLR3. And the main point is that it tries to simplify or structure the channel of the availability of these resampling methods, because beforehand, there was no package putting it all together. They were in the same way as the learners, multiple resampling methods spread across different packages using quite some different syntax as well. And it was very hard to use them, if not partly impossible, in a framework. And you had to adapt not only your data to the learner, but then your learner to the resampling framework, and then putting it all back. But then you couldn't use any framework capabilities. So this puts it all together. Again, same syntax. That's the key goal. And there's also a submitted article about the package to JSS right now. So what does it offer? So
is that article online?
It's an archive, the submitted version, and the submitted one is still in review right now in JSS. The package offers also generic autoplot functions for all the resampling methods. So that means you can visualize in 2D space and in 3D space your resampling methods. Why 3D? Because when we talk about spatial temporal methods, of course, we are in 3D space, and you also want to have a look at them potentially. And for this, we use Plotly internally to give you a 3D visualization of your data, how it's resampled in a 3D space. Currently, we are wrapping 8 resampling methods from these packages, including the one from Hannah Meyer, which we'll talk about in the afternoon, not about the resampling method per se, but about your spatial temporal package. Maybe she'll also mention and use one of the methods there. The BlockCV package by Valavi et al. In 2019, it's very popular. As far as I know, many use it standalone for their modeling parts. But if you want to use it in MLR3, you can also do it via this package. What is the take actually about spatial temporal resampling methods and about performance estimation? So what is very important to know in the first place is that so far we've talked about resampling, benchmarking, and everything else without spatial data, with most often usually using random sampling in the cross-validation, so non-spatial cross-validation. The point is that non-spatial resampling is known and proven to overestimate model performance due to mainly a spatial autocorrelation between the training and test data. So you have to envision that if you have spatial autocorrelation means that if 2 samples are very closely located in space, they are quite similar. So if you envision that, for example, on a soil level, right? If you have soil and you'd use one sample from where you stand and then 2 meters apart to the right, the probability is very high that they have the same value. So if you now put one of those 2 samples in either train and test, well, they have the same value, and then in the end, your train and test training sets are highly similar. And what does that mean? If your training is very similar to your test, well, your model won't have much of a problem to predict the values and will have a very good performance in the end. But this is just because of the autocorrelation fact that your samples are autocorrelated and are very similar to each other, and actually your training set is much similar to your test set. And usually, when you then do the final prediction to some other area, the location there might change, the environment is different, and your soil is much, much different. So then you do a prediction and you say, my model, it's so good, and the prediction, of course, I resampled it, is so good. I predict it now to this other area. I'm very, very certain that I've done some good predictions, and these are the actual soil values at this new location. But this is actually wrong, right? Because your model is that good because you actually trained it and tested against it with the same data. But if you predict to a very new environment, things are much different, and you probably have a very bad, may have made very bad predictions, but you don't even know. And if you would test this in a proper way and have some test data actually to verify it, you would see that you have a very high overestimation in your resampling compared to how good your predictions actually are. And this is because of the autocorrelation. And now we need to deal with this kind of thing. So usually we split our data between train and test with what we have at hand. And the problem is that it's hard to get around this, right? Because how do we split our data that we make sure that they are not so similar and actually match the target prediction case that we want to apply it on? So if we want to make a prediction on an area that's actually, 500 kilometers away, but our test and training data are very close to each other, that doesn't really match. So it doesn't really match the thing that we want to apply the model on. So we need to make sure somehow that our a resampling test and training scenario mimics what we want to do with the model introduction. So, and there are now certain ways to try to achieve that. And I can already spoil you, there's no perfect way or no unbiased way so far, at least, to do that. And what we at least know that we want to tackle this in a way that we don't have a high overestimation of our performance compared to what we applied on later. But of course, all methods that we do apply for the resampling and other potential threats to the model and the resampling per se might either result in a true performance, but we actually don't know what actually is the truth, right? Or it's often hard, or it might actually result in maybe an underestimation of our performance. So there's no real single solution to that, but at least spatial resampling methods are one approach to tackle this and one approach to potentially reduce the overestimation. Doesn't mean that the result is close to perfect then, but it's one approach to do that. The key thing to keep in mind, and this is also the takeaway of the slide maybe, is you have to ask yourself, what do you want to predict? Is your data grouped? And how can I mimic my actual prediction scenario that I want to do in my resampling? Is this a fair comparison? Or is this really doing what I actually do then in practice? So Spatial TempCV provides you with resampling methods for spatial data. That means instead of doing a random clustering, each of these methods somehow takes into account your spatial location of the points and does some group segregation of your training and test data, or even blocks specific points and removes them from the data set at all. They are not in train or test at all. So all of these have different approaches to tackle these. So, and this is what we, a selection of what we offer. So you see that first, there's always a repeated method and a non-repeated method for all of these. But let's focus on the last part, because so these are actually the unique ones then. So we have spatial block resampling, spatial buffering resampling, some k-means clustering here, some so-called disk resampling, environmental blocking. This is happening in the feature space and not on the coordinate space. Some tiling, which is similar to block resampling. And then we have two spatial temporal methods that operate in the 3D space. One is provided by the Pluto algorithm, which is actually a proprietary one from 2001, and don't really recommend to use it. And the website is also down in a while. And then there's currently only other spatial temporal implementation from the CAST package of Hannah Meyer with the spatial temporal leaf location and timeout resampling. Yes, Tom?
When the blocking, you have to provide the blocking argument. It's not that you generate the tiling system and then you do spatial.
Exactly. So you all of these methods have some arguments, and they expect you to either specify whatever they do, either some blocks, so they create a grid and then you specify it in the grid, or you specify how you want to do the k-means clustering, for example. And sometimes, so there. Okay, I come to that later, but each of these
because like one of the big thing is how the size of that block, the tiling block. So if it's a big, you get a very different out if it's very small.
Of course, yeah. Each of their methods might not fit your data set at hand, and it depends on how your data set is spatially structured and located and what the method does. So there is also not, let's say, an easy solution of choosing a method, but I'll come to that later. But all of these methods, of course, apply certain heuristics and assumptions on maybe what they do and what your data might look like. And some methods might fit some data more or less. So the choice of these methods is not easy, and there's no easy solution to that. And there's also, even if you have made a choice, no easy solution on setting the parameters. Again, in the end, what is the important part is how can you ensure that your resampling scenario mimics what you want to do in the prediction case? How honest is your resampling? Because you can always cheat on yourself. You can do whatever you want to do in the resampling. I mean, the worst thing probably is using non-spatial CV in a very clustered data set, because you have a performance of, I don't know, almost no classification error. And you can say, oh, that's great, I did a resampling, you know what, I got this number, and then that's how we roll. Then you do the prediction. In the end, make sure, what is important here, everything you get out are numbers. They can be meaningful and non-meaningful, but you have to make sure that they are meaningful for the task at hand and that you can justify this to some degree, right? Of course, in the end, there's no perfect solution again, but it's important that you've thought about this process. Right, so besides all of these methods, there are some built-in options in MLR3 core that allow you to group some observations that you can actually use in the case of a spatial data scenario. And this is supported via the column roles and specifically via the group column role. So what are column roles and what is the group column role? So if column roles are attributes in a task, and they tell the task how specific features are being treated. So you can, for example, say you have a column role that specifies your features and here and though, or you have a column role in a group that says, okay, this group, this column is a factor variable, for example, and this specifies some grouping. So I don't want to use it as a feature. I want to use it as just for some grouping, right? Columns can also have multiple column roles, so they can be used for grouping and as a feature. It's your choice. There are multiple column roles in just a group one, but this one is of interest if you do spatial modeling, because as it's written here, features of a group that is specified via this group column role will always be together in your resampling, either in train or in test. That means if you have, for example, you split your resampling in 5 folds, and you assign here a feature that has 10 different groups, then these groups will be split across your folds, but it will be made sure that the groups that are grouping the observations are either in train or test. So for example, you have to split those 10 across those 5 folds, but it will be made sure that, for example, every observation that is of group 1 will always be in train or test at the same point. And there might be 2 groups actually, cluster-wise, but then they are spread like this. And this method is actually a mix between using fixed groups completely, but allowing you to resample some stuff for fold variety. So that means in the first part, if you have more group levels than folds, you are able to create multiple or different versions of your folds because they are spread across the folds, and you can actually do some repeats and a mixture of fixed groups, but still being able to use a flexible resampling with repetition to minimize variance. So this is the groups count, and this usually can help you to group features and distinguish them between train and test. So they are not within both, and by this you have a spatial separation between your training and test sets, making it harder, quote unquote, for your model to just easily predict or achieve a good performance. Then there is another resampling method directly from the MLR3 core package, which is the custom CV, which means you can use a fully predefined resampling scheme. Of course, you cannot iterate on that because it's just using one fixed set of folds. You can either supply a predefined list for training test, or you can use a factor variable that fully predefines this as well. So a factor level, for example, with 5 different levels will result in a 5-fold non-repeated cross-validation then. And you can, of course, also then make sure that this matches your spatial grouping in the data. This might be helpful, but maybe you want to use the groups feature again to have a bit of variety there in the resampling. But sometimes it's okay to use this, but keep in mind that you don't have any repetition then that you can use, and this you're relying on four-fold estimates for your whole performance estimation in the end. So next one. So one slide, and I want you to know this, but we are not going into details because it's a very complicated discussion as well. But there is an ongoing debate right now since a few years whether spatial temporal resampling methods are actually too pessimistic. Right? We talked about non-spatial resampling methods being too optimistic, and this is acknowledged by everyone. But it might be that spatial resampling methods that we try to tackle this problem, and we know we are not perfect there, are actually way too pessimistic. So if you report this performance estimate at some point, and you maybe also do a non-spatial resampling, you have a big gap between both, and you don't know what should you report, and maybe you can report both, and you don't know the real truth. But people claim that, okay, usually if you do that, you will always be too pessimistic. So they say, don't use that, which is, of course, a fair claim. But if you say don't use them, what do you do else? And so these people in the papers here, they came up with some solutions for that, but some solutions of that only apply to very specific use cases where you have a lot of data and can take a probability sample and whatnot. And they have other approaches to do that. And to get a full discussion of the whole topic, I highly suggest just to read papers and to follow up maybe on additional discussions in the future. And it's great that we have some discussion going, and everybody knows that spatial temporal resampling methods are not the complete solution to the problem, but there is not yet any other solution being found. And it's great to see new approaches and discussion being happening. But that also means that using spatial temporal resampling methods is not a problem or bad at all right now. So in terms, it always depends on the structure of your data, how you can split your data and how it applies to your final prediction use case. And there is nothing bad in doing so. It's like using spatial temporal prediction resampling methods is definitely better than using non-spatial in most of the parts when using most of the applications when you use spatial data. Let's see what comes out of this discussion, and maybe we'll have some advanced approaches that find a middle way. Maybe we just find a good approach for specific niche use cases. But I just want you to be aware of this discussion. Yeah.
But the message of the first paper is spatial cross-validation is not the right way to evaluate NAP accuracy. So it's very clearly saying it's basically wrong.
It's very clearly saying that, but there's just a strong statement doesn't mean it's always right.
The title is wrong.
Yeah.
Submitted it.
So there's also the second paper, right, from Etzer and Hannah, who partly tackled this as well, and other discussion going around. And it's always a question of how you phrase it and what's then what you present and what's inside. Of course, you get a lot of attention, of course, also if you use that title, it's not bad. But overall, I would say this is an ongoing discussion, and there are two sides, and they have both their arguments, and they try to evaluate this. And probably there needs to be some communication happening as well to get both sides on the table, maybe. But in general, I would say it's interesting that something happens and that we talk about this. And everybody can also just make their own minds of by reading the contents of the papers. And so I highly encourage you to do that. Those are the three main papers that currently contribute to the discussion. Maybe I missed some, or there might be more in the future, but these are definitely worth reading, and including the ones they cite from the past that they make their claims on. So yeah, but I'm not the person to make a judge being a judge for that or make a final statement on this.
But what would be useful to take, multiple data sets and look what happens, like with the proper benchmarking, not just speed wise, but statistical accuracy, etc. And to benchmark and see really when does this happen that you're over pessimistic, you underestimate, you overestimate, whatever. That will be interesting. And I looked at that, so I'm starting to work on that. And hoping also to get the paper out to zoom into that more, because for sure there's a difference between spatial blocking for fine-tuning parameters, spatial cross-validation for relative mapping accuracy, so the different phases, and depends how you implement it also, whether you use little blocks or you just want to block repetition, or you use a large block, so you really want to check like really big time extrapolation.
Yeah, definitely. So there are many details to be aware of, and well, it's a complicated discussion. So it's not easy, but given also that we mainly focus also maybe on the points and the framework provides you here and there, I don't want to go in too much detail here, so it's a complicated discussion.
Our previous summer school, we have Harold Kuvelink explaining this idea that if you want to just evaluate the map accuracy, just get the mean error, then the most correct thing to do is probability sampling, so like a simple random sample, because everything else would be biased.
Probability samples are always nice to have, but usually you don't have the data for it.
This is correct. You don't need to.
Yeah, sure. But
you need to do any spatial blocking. You just do simple random sample, and you will get the most accurate estimate. And it is really correct. I mean, he shows it. With the he put these balls in the rocks. I don't know, in a glass or something, and then he shows. Imagine if it was cluster or if it's purely random, if you do simple random sample, you get the correct estimate. So that's correct. But it gets different when you do modeling with the cluster points. Let's say your points are clustered, which is many cases. And then you want to fine-tune and get the model, but without overfitting. And if you don't do spatial blocking, then you're going to overfit. And if you overfit, then your predictions will be off. And I looked at that, and and I knew that, but so basically, spatial cross-validation is the right way to tune cluster data sets. It is the right way. And in a way, when you tune the cluster data set, you also do kind of cross-validation, because you do this resampling. So it's this title, yeah.
Yeah, I mean, the title is also tackling a very generic term of doing things, right? Which is maybe the main problem of this title, because it always depends on the data, how you do it, with what kind of approach you tackle it. And spatial cross-validation per se, saying this is wrong, is too big, right? And I think some of the follow-up papers here also acknowledge this a bit, and that also say that the claims in their first paper say that it's not feasible to usually take a probability sample, and it's not feasible in practice, and we need to find other approaches. So it's an ongoing discussion. I highly encourage you to read it, and maybe also talk to the people, Hannah and Etzer. They are deeply involved, more deep than I do, in this discussion, and it's good to have it on the radar. So let's move on. Let's have an example how you do spatial cross-validation with MLR and with MLR spatial density. So here, for example, we use again a forest. We predict landslides events in Ecuador. We use the SF package to read in some point data. It has some coordinates. It has CRS. And we can have a look. This is just a simple feature output here, as you might know it. You see our CRS information, some features in our bounding box. We can create a class of ST task in this case with the converters. We give it an ID. We set what target we want to predict. We set, in this case, what the positive class is. And then we have our task, right? Same printout almost as we know it from a normal class task classifier, with the difference that the task classifier ST also prints the coordinates to the screen for us. this is just some additional information. It's nice to have, so you know you're in the spatial task. And by default, again, the coordinates are not used as features. So let's walk through it. We define a learner. We said we specify that we want to have probabilities returned. We create our task. We say here, this is actually then now the important part. We say our resampling should be repeated spatial CV chords. We set the amount of repeats and our fold count. And then we pass this to the resample function with our learner, our task. And then we get a resample result. And this resample result, we can call the aggregate method. We give it a measure, and it will return us the aggregated measure of our resampling. And here we have a classification error returned. All of this is pretty much the same syntax as normal MLR3 with non-spatial resampling. The only important difference is that we set a different string or character input here for the resampling, and we say we want to use spatial resampling instead of a non-spatial. This is everything you need to change. Of course, you need to probably configure some of the spatial temporal resampling methods and how you want to have them constructed, but that's as easy as it is, so to say. If you have a resampling created in a spatial sense, you can visualize it. So we have the autoplot function, and you give it the resampling, the task, and then you can subset the fold ID, you can specify the point size, and the second and third lines here are just that we have some nicely formatted X and Y axis with respect to the coordinates. And you see here exactly how your train and test folds are aligned in space. So it's a very nice overview for all the methods to just get a feeling of how your data is split. Because without this, you make some images in your mind and you think, yeah, I do this like in space, and then I split and I cluster them, or I block them and I take some points out. But this actually gives you a visual representation of how it looks like. Of course, what we do here is we use the coordinates that are inside the task, and then we just use the instance split information of the resampling to create this. And that's actually it for the spatial temp CV. So you have the autoplot, you have all the different resampling methods. And by the way, you can also apply the autoplot method on a non-spatial resampling if the task has coordinates. So if you apply it on a non-spatial resampling, you will see that this is just a very scattered way mixed between training test points next to each other. So you can nicely compare your spatial resampling to a non-spatial resampling and put them next to each other and also align them as you like. Because in the backend, we use the patchwork package for easy alignment of the plots.
What is it? The pipe operator? This multiplication?
Sorry?
This pipe operator, the multiplication sign?
Yeah, this is a syntax from the patchwork package. That means apply this scale by continuous change to all subplots. So because we have two plots here, and by this we just say we want to apply this to all of them. So this is done by the patchwork package in the background. Yeah.
It's a ton of I don't know what the object is for patchwork, and then can you just add other plots to it?
Yes, the output will be a patchwork plot output, a GD plot, and you could then use this and modify it in a patchwork syntax with others and potentially create any complex output formats in that sense. Yeah.
Could you also plot these as like SF objects to get like more context of where these points are in space to like your study area and stuff?
To plot these as SF objects.
Add a GD plot later.
You mean like lines or something?
Yeah, so
Over
like
there.
see if your points are like falling into like your different, like, you have like outline, like polygon outlines of your study area or something.
Okay. So I don't think with the auto plot, because the auto plot is more or less like a predefined, opinionated way of displaying this. What you would need to do is then manually take out the coordinates, manually take out the resampling groups and build it together yourself. Because yeah, we don't know what other like SF objects, for example, as you said, you have. And it would probably not so easy to as well to overlay them just here. So because this is just like, let's say a very opinionated default plot of what you get. But I mean, you have all the information in the object, so it's possible in the first place, yeah. So, right. So before we conclude this part, and let me always took 1 hour, I will also have some hands-on definitely, and then Leandro said that we will take about 30 minutes. So let's see how much hands-on we have, but we'll definitely have some. So there's a big spatial temporal analysis chapter in the ML3 book, which tries to summarize most of what I said. There's also a function reference, and here's some literature that addresses exactly what I also presented here in the presentation. And what actually about spatial temporal methods? So I said there are 2 in the package, and you can denote them from the others because they have this T inside here. Instead of SPCV, they have SPTCV, spatial temporal CV, and they support both spatial and time information in your task. In general, the thing is, if you go 3-dimensional, things get quite complicated. It's much complicated, much more than just having a 2D space. And we need more help and also expertise in dealing with this temporal part, both in the resampling methods, but also time series and whatever else there is with ML3 temporal. I said this in the beginning, I'm saying it again now. If you know somebody who yourself are interested, feel free to contribute. And thanks to Marek Becker at the end. So this is the guy who is doing this with me in the tandem. We developed all the spatial stuff in MNR, and he's also doing a lot for the tuning in MNR per se, and he's working as a research engineer at the LMU in Munich at the chair of Bernd Büschel. And thanks also to all members and contributors, and to the OpenGeoHub and Synchro for sponsoring us, so we can have some workshops at least once per year. And yeah, in general, thanks for you being interested in MLR. I hope you have some points to act up on, and maybe to use the framework, and some reasons now. And before we start into the blog, so that's where we're currently at. So there would be now a bit of hands-on tutorial for the spatial part. And then, of course, we don't have 1 hour left, but there would be one use case example from Leandro. So Leandro, what do you think? So now we have 30 minutes left. If I do 1 hands-on for the spatial at least, and then you have like 20 minutes left or so. Is that good?
Go ahead.
Good. I think we still have some Q&A. Okay, we skipped the break, and I just have a look at the Q&A quick. I think this was from the first book still for the presentation. Is the computation performance of MNR3 comparable to scikit-learn? Even better? Yeah, we have some comparison, but I think it's outdated. We should do another one. And I can't really make a comment on that. I'm sure that we are not, there are not much difference between both. I don't use scikit-learn on a constant base, and I get this question quite often. So maybe we should do a regular benchmark on this. But in the end, it's your choice what you choose. Choose the framework and the language you like. Don't just go for speed. Also go for other things that are available in either one, and where you have support and feel familiar. The same goes for tidy models versus MNR3. Again, all do the things quite well. Different approaches, different syntax. And one will always maybe a bit faster or slower than the other one, but not in those margins that you really have to maybe switch over and ditch everything you did before. So then let's move to some hands-on. I mean, the hands-on is most mainly just the same as I showed you on the slides. What is maybe most interesting is if we have a look at the spatial parallel predictions, rather than clicking through the basic examples again. So we'll do that right now. You can find this in the ML3 spatial parallel part. And if you switch over from the first block and from the first one, just open the project. The other project in the hands-on part in the root, restore the RNF environment, so you have all packages, and then you should be good to go with a clean environment and a clean state. There's this hands-on the project, right? If you've already cloned it, you can just check that out and then eventually hit RNF restore if it doesn't restore you automatically, and then you should have the environment that you need. So at the top, we load the packages, we exclude some from future just to avoid some warning messages here in the console. We also set quiet execution via the logger in MLR3 because we're not interested in all of those outputs right now. And here is just we create some arbitrary raster stack via this MLR3 spatial function. You can set the size and don't worry about the errors. They are caused by Terra internally. They are actually not errors because you still have a valid Terra object afterwards. There's quite some discussion about this in the package, but it's happening since its existence. But you have a valid raster stack in the end. And we can query the number of cells. And you see we have quite some cells in here to predict. So over 1 million, 1.2 million. Here we create a sample stack, and you can adjust the size as needed. So if you use a bigger one, you get bigger vector here for training, and the same for the generate stack. We create a classification task, spatial temporal. We set our targets here accordingly, and you can have a look at the task again. So we have some coordinates in here. We have just one feature, right? It's just for demo purposes. Yeah, it's a two-class task here. We use a ranger, again, without training. Usually you would tune it, without tuning, usually we tune it. So we tune it on the task. And then we do a bit like modification on our raster stack. We remove the target variable because we want to predict it, of course. Usually you don't even have target information in your prediction image. We create an unsupervised task using this image, and we give it an ID. And what is important now to trigger the parallel prediction is that we set this feature flag within the learner. So this parallel predict flag is usually false, and we need to set it to true to tell the learner to use parallel prediction. Then we use the normal future syntax to initialize parallelization. So we say, please use the multi-session plan from the future package. Use 2 workers. I use multi-session here because multi-core, you cannot use it in RStudio because forking is not supported. You can only use it in non-RStudio environment. And you can, by the way, also not use it if you're using Windows. So if you're using Windows, you have to use multi-session or call R backend, which I'll show later. So let's do this and execute it. And so now we are running this in parallel, but we don't have any progress, right? Because I turned off the progress messages. And I haven't yet triggered any parallelization with the progress R parallelization output with the progress R package. This is something that is not yet supported in ML3 Spatial, so we still need to add progress R support for the predictions. But now we are finished, and now we have this prediction object here, and you see again it's a SPAT raster object, and it has the values that we wanted to predict in it. So we went from some vector data input for training, using then an image for our unsupervised task. to predict on using the predict spatial function, putting in our learner here and the predict task, and then executing everything. So you can, I won't run this because again, this does not run, or it will run in RStudio in fact, but it will tell you that it's running sequentially. So it's not using parallelization. What you can do and what is might be of interest, what I haven't shown before, is with Future, you have available the availability to use other backends as well. So for example, here you can use the call R backend, which is just a different approach of parallelizing things by using multiple remote R sessions running in the background that are differently connected and talking to each other than using forking via multi-core and using socket-based parallelization via the p-socket way, which is multi-session. And there are more backends available for Future. You should just check them out and decide for your own that you like. Each of them has pros and cons, but this is the Future call R package that is needed for this backend. So we load this package, and then we say, okay, we want to have the call R plan. And then we do the same prediction again. And depending on certain points in the backend and how your data and the overhead of your computational CPU multi-core performance, one or the other backend will be a bit faster or slower. Just check it out. Sometimes the call R backend is really fast and almost close to multi-core, and you can even use it on Windows sometimes as a good replacement for the multi-core backend. So this is actually the same thing as the other one before. And now we have our prediction object as a spot raster, which we can do everything with. Right, so now this was, I know, quite a bit of rush to go through, but now we have, 23 minutes left. And I think this would be a good time to, you have all the other practical parts in here that you can click through and use as an example how to do it. Maybe a good time to wrap it all up on my side and take some questions beforehand, and then afterwards hand over to Leandro. So questions from your side, yeah.
So what is happening with the ASCAP unsupervised? Is that unsupervised classification? Because it looks like you're predicting, like classes rather than clustering based on fitted values. So I think that is supervised.
This is some internal thing we need to do for now. So we need to pass a task rather than just giving and handing over an image. And we can't use, so internally for the prediction, specifically for the spatial prediction, and we can't use a supervised task because we usually don't have a target for here, right? We just want to predict something. So this is more like a bit of cheating, and it's not about clustering anything or really doing an unsupervised classification here. So just in practice, you can just more or less ignore it. It's more like a bit of not so nice syntax right now. Maybe we will change this in the future so that you can, instead of putting a task in here, right, just put in your stack directly. But for now, it's like this. And I'm aware that this causes confusion. I'm aware that this is not so clear because usually this could be a nice predict new data directly on the data call. But there are some internal reasons how MLR3 operates on the objects, and in certain cases it requires a task, and we require a task to be put in up front. I know we could potentially handle this internally to create the task, but as far as I remember, and there were some reasons why this is problematic. And I'm not so clear about the internals here because this is something marked. So he might actually be the person to better comment on that. But for now, for practical reasons, I would just say don't think too much about it. Just ignore this. So so I think you can just play around a bit as well with the backends and whatnot and what is best for you here, and just see how this works out for you. And if you face any problems, like for the inputs, for the parallelization, if you see some errors, some other things, open an issue, talk to us, contribute. We need your input, what works, what doesn't work. Of course, we have our examples, our test cases, they cover a bit, but they certainly don't cover every niche use case that people could use spatial images for predictions. And we need your input to resolve all of those and make it better. Right, so is there any in the Q&A in the chat? No, I don't see so. So are there more questions from the audience?
You can also ask them in the MetaMost. There's actually lots of questions popping up there, but you can
Okay.
But maybe for the sake of time,
yeah, exactly. So I would then thank everybody for listening in both sessions or just in one session. I hope you got an idea of MLR in the first place, what the framework provides you, and also what it provides you with spatial data and extensions, how you can use it for yourself, how you can potentially simplify your modeling. Try it out, play around with it. Maybe you like it, stick with it. If not, that's also good. There are so many ways to do modeling and learning in R and other languages. If there's anything, talk to us, and thank you for listening, and see you either on GitHub or somewhere else. Thanks.
we disconnect the.
Okay, yeah, I think it's connected.
It's all good.
Yeah,
Thank you very much.
share my screen.
Yeah. It's working.
Okay, so thank you very much, Patrick, for this nice overview. And yeah, basically I will show kind of workflow that we are implementing to do modeling with MLR3. So I shared the link here, and yeah, I'm not really like highly skilled with R, so I didn't create a R markdown and like a proper tutorial, so sorry about that. And the way that the code is structured here, it's basically I created a few wrapper functions here, and actually there are just 3 functions, but the main function is this one, so multiple parameters. But it's this function train MLR3 model, it's basically a kind of implementation of this workflow. And discussing with Tom, I thought that might be a good idea and use the hackathon data and kind of repeat what I showed yesterday for modeling with scikit-learn. But yesterday I didn't present anything related with ensembles, like really combining multiple classifiers and an estimator. So, but in the UMap you have a tutorial for it, and actually here I'm using an ensemble. So basically, what I will present is the execution of this workflow, and considering the hackathon data set, the train data set, and basically the workflow is composed by these 4 main steps. So considering the samples in the covariates, the first step is a feature selection. And what is like for me, feature selection is a kind of one first step, but you have several approaches to do it. And the function that you have, it's flexible to use several approaches for each of these steps. So it's a kind of, for me, what we have like genetic search for feature selection, a kind of instance of the one way to do feature selection that I will present, but you are flexible to use all feature selection options available in the MLR3. So basically, we will do a feature selection considering a genetic search and a hyperparameter optimization considering a random search and a space of parameters predefined. Model evaluation with 5-fold blocking cross-validation, and the blocking here, it's the tiles, so we can assume that it's a spatial cross-validation. For the train data set here, for the hackathon, it's really important because as I show in the first day, you can, if you remember, the samples are really clustered. They are all inside of one tile, and you have another tile really far away in the space, and they are all clustered there. So it's really important to avoid do the training, the validation, and the cross-validation, considering samples that are really inside of the same tile. So either you train with all the samples from one tile and validate with another one, or the other way around. So that's why it's important to find the blocking CV for this specific example. And the final model, it's training using all the samples. So considering it will train like the output, it's the trained model, it's ensemble machine learning. I will talk about it. The CV predictions, again, I like to have the CV predictions, all the ground truth data and all the predictions considering the out of fault. So you have full flexibility to derive any metric. So for me, that's a good approach. And the variable importance considering the random forest, but depending on the estimator, you can also have for the XGBoost. So basically, what is an ensemble machine learning, the way that we are applying here, it's basically one first level of classifiers. So here it's random forest, graded descendant trees, and GLMNet. And using these classifiers, basically you can predict probabilities. And here it will be a binary classification. I will aggregate the class. And you can use these probabilities to train a kind of second model. And here it's a logistic regression. So a regression applied to a classification problem in the logarithmic space, basically. And the output, it's also probabilities. So when you have this kind of 2 levels of classifications, I will show it in the results, but the second one, it's kind of prioritize what classifier has like more occurrence. So it's a good way to balance and integrate all these classifiers and generate one single prediction that use the best of all these all the first classifiers. So let's execute the code. So yeah, will increase a bit more the font size. Don't need this stuff. So basically, there are several packages here. All the packages I already have. If you want to reproduce it, probably you need to install these packages with this line. And here I'm importing everything. And now, this line is just to bring the functions to the scope, so we can use mostly that function train MLR. So here it's just a way to download the data. So I presented this function in the first day. So here basically I'm reading a Parquet file, but not straight from the cloud. I'm just downloading it locally. I have these files. So and by the way, for the people that had problems with the Parquet format, I uploaded a CSV version of this file, so you can also use it. But here I'm just reading the Parquet data and the data in the Parquet format. And yeah, mainly we can see the train data, the train data, the validation, and the test. Number of samples, number of columns, and as you already know, we changed the test data, so we removed the class label to compute the metrics on our side and the expected value. So you have 3 columns less. Okay, so now we have the data, and basically what I will do now is starting the definition of several parameters that we will send to the workflow function to train MLR3 model. I will explain this. But first, I will prepare the data because for sake of simplicity, I will reduce the problem to a binary classification. So, and I will do it in the train and the validation data. So basically everything that it's labeled with 3, it's order, I will convert to 0, and the 2 grass class I'm converting to 1. And we have several columns. This data set, we did the overlay with really like a large feature space, but I will not train a model using all the features here. I will just select the Landsat data. So this is a bit different of the tutorial yesterday. Yesterday in Python, we did the space-time overlay here. I will just I will not present the space-time overlay in R, but just use what we already have to run and go through this workflow. But I passed it maybe too fast. So here we have the target variable and the group name. So basically this, the first column, it's where we will have the values to train the model, the expected value, and the group name, it's actually the column that we will use to implement the blocking and the spatial cross validation considering it. So to train train the model and validate with samples that are located in a different tile, not use it to modeling. So here I have like a list with these 2. I'm calling like model names. It's not exactly the features. And basically I'm selecting just 500 samples to reduce the training time. And I'm selecting just the features of my interest here, just the Landsat data. And I'm removing the NA data, and I end up with 500 samples and 86 columns. Remember that we have 1 column to define the predicted value and the expected value, and 1 column to the group name. So to run the space cross validation. Here I'm defining the number of cores. So I'm actually using and training the models. I'm using the prioritization inside of each learner. So it's not I think it's not actually the best way to do for this example. I probably should use what MLR3 can offer with this future in the session. So to parallelize all the resamplings. But we did like that because I started developing this code and this workflow to do predictions, and we noticed that there was like a improve in the predictions, and maybe we need to update the way that we are doing the predictions on a raster data. If we don't like set the number of cores for the models, but yeah, as Patrick also showed, we can set it later. It's just the way that it's implemented now. So this is really important. So I will show the plot here. And where is this? Yeah. Here, where is the graph? Okay. So this is one way, because now we are using that. Here we are creating a pipeline. So basically, the way to implement ensembles in the MLR tree is through pipelines, and you can do really whatever you want. You are quite free. So, for example, we can add like some feature reduction and approach before the first classification. So you can really define a complex pipeline here. But what I really like about it, it's just one single object. So, for example, here it's basically like a union of different learners. So, for example, if you want to add an additional learner, it's just add a new row here. And of course, you need to define the learner model, the predict type. So there are some parameters specific for each learner, but it's one single object that defines your whole workflow. And here it's a feature union, and the last step it's a logistic regression. So what we call a meta learner. So, but you can add, for example, I don't know, a PCA before to do the classification and the training with this learner. So you have quite flexibility. And one thing that it's important, so this is just like a graph representation, which each operation, it's like a node, and you have a connection between these nodes, but you need to convert it to a learner. So you have this method as learner that will kind of wrap all this pipeline and transform in a learner that can be trained by the MLR tree. So basically here we are implementing the feature selection. I'm using this approach here. It's a genetic search, and basically it starts with a kind of random selection of features, but slowly it tries to create some what they call like mutations, and really change the selection of features according to these small like oscillations in the original population. So it tries to follow the kind of the evolutionary theory. It's not my field, but I think it's a nice approach, and sometimes could like really find the best features in like way faster than more old-fashioned approach, basically. And here it's that there are some parameters to tune it. The most important is this one, the number of iterations. But to do it, you also need to have a kind of learner, and I'm using just a random forest because it's out of box learner, and to do this genetic search. So, okay, so this is the first definition, and here it's the second step. So to do the hyperparameter optimization, we have, again, this is considering this pipeline, it's one single object, so you need to you can define all the parameters that you might use in one single search space. So here it's just a kind of distribution of values that will be selected randomly to train your model. And I like also it because you can put all the hyperparameter distributions in one single object and send it together with the pipeline. So basically, this till now, we just defined stuff, and I will start the training. I think it's about 2 minutes, and I will just explain what the parameters here and how it works. There are some problems that I would like to explain, but first I will start with the first parameters here. So basically, yeah, we are sending the data, the input data, and we need to say what is the column that we want to use as target, and the learner, like a wrap for that pipeline. This is the metric that we are using to optimize, to select the best feature, but also the best parameters. So here we are using a log loss. It's a metric specific for the probability. And here we have the feature selector. So basically the genetic search we are sending here, and MLR like really splits it in different objects. So we can have one approach to do the feature selection, but different strategies to execute it, and like to, for example, define when it will, how it will split the data. So basically, it's the approach, but actually this thing here, it's defining how much time it will run. So this parameter, not the number of iterations. So it's basically running for 2 minutes the genetic search. And for example, if you want run like more time or less time, it's just changed this terminator associated to the feature selection. Here it's the resampling strategy, 5-fold cross-validation, but we are sending this group parameter that actually defines that we should use the tidy ID to really select the train and the validation during the cross-validation. Here it's the same structure, but now for the features, for the hyperparameter optimization. And for the hyperparameter optimization, it's just use 10%. You can define it, and I will show it in the messages. And the same strategy, you have a terminator when you should stop. You have a resampling strategy. Here it's just a random search, so it will randomly test different hyperparameter values. And this is the object that we created there. There are some log messages here to present the progress. And here it's the validation resampling, but in the last step. So let's see what we have till now. Basically, we tried to find what are the best features for 2 minutes, and we end up with 12 covariates from 84, and now it executed the hyperparameter optimization. So maybe it's too low, this number, and so it's 50 samples for different combinations of parameters, but you can increase. The validation occurred, so we executed a cross-validation and we trained a final model. So now we have it, and the object that it's returned here, it's just a named list. So we have the learner, the feature selection result, and the cross-validation prediction. So you have ground truth and what was the predicted value. And from now, I'm just like calculating some metrics related to the cross-validation, and later it's just the same metrics, but for the accuracy, for the validation data. So I will not like explain all these metrics. I will go straight to the validation data, but there is one important thing that I would like to show. So this is actually the summary of the meta learner. So as you can see, it's logistic regression, and here we can see that kind of the performance of the 3 learners, and as expected, the XGBoost and the Ranger, it's performing better. Maybe we could improve the GLMNet, tuning some parameters, or maybe there is something that we need to do with the input data. I'm not sure, to be honest. and we used it for a different data set. And for the hackathon data set, maybe there is something that we need to change. But you can analyze it and really see that in all this workflow, the output of the 3 learners were actually used to train a second learner, and we call this whole structure as ensemble machine learning modeling. And I will skip it. I will just go now to the validation for sake of time. So one thing that is interesting in the result, you can see what are the best variables. So the result of the feature space, and I'm just getting for the validation data. We already did the reading in the beginning. So I'm just now, instead to read all the columns, I'm just use the columns that were selected as like the best one, and actually the columns that were used to train the model. I'm calling it as new data. So now I have just like a data table here, data frame, just with 13 columns, way less data. And I'm predicting it using the predict. I think there is other way also to use. You can call the predict of the learner. But I said, I send like the predicted type as probability. So now I have the probability to be 0 or 1, just 2 classes. It was a binary classification, and the expected value. And of course, the expected is 0 or 1. And you can derive some metrics, like you can plot the Hawk curve to see like the probability, and you can calculate the area. And this is for the validation and data. It's not derived from the cross validation, but it's actually derived from for the validation. And you can do the same prediction. You can also derive it directly for the probabilities, but here I'm just doing another prediction without the probability. And I can calculate the confusion matrix and this metric that it's really poor considering the results of the classification. So it's just a demonstration of the workflow considering this ensemble machine learning, but in a way that now, for example, you can play with the parameters and really, for example, remove one of the learners and try another learner, or improve, for example, the feature selection. And of course, the first thing here, it's actually use it for all the data set, instead to just use like a 500 samples and all the covariates here I just selected. And the last step, it's just saving the variable importance. It's not here actually. It's on the top. I need to check it. But you can save the model and you can do like predictions later. So yeah, that's all that I have to show. Of course, the next step here would be really use this model to do a spatial prediction. We are still really struggling with that. So I was discussing with Patrick. My goal, it was actually really do something similar of what I did yesterday, access the data in the cloud, just retrieving a very specific bounding box and do the prediction. So I will discuss later with Patrick to maybe create an issue for it, just to like predict kind of cloud optimized geotips, but for very specific regions. But also we could have like small tiles locally to do the prediction. That will be my next step here, and I will try to provide like a example of the prediction in the repository, so I can keep you posted through Mattermost. And yeah, we are 10 minutes out of time, so we need to stop.
But it's great, and it's as I said, it's on Leandro said it's on Mattermost. You can see it, and we will be working with Patrick, trying to do this to work for global good. We are producing some global data sets. So we're looking really forward to it. And yes, but officially we're still using MLR, by the way.
Whatever works.
So thank you. Let's stop with the